Okay, so John is the director of analytics at QxBranch. He's leading the company's development of advanced data analytics technologies. Previously, he was the technical lead for corporate data analytics at Lockheed Martin. John has experience applying machine learning to a diverse set of domains, including healthcare, supply chain optimization, and program management. He's completed his Ph.D. in electrical and computer engineering at Carnegie Mellon, where his work focused on machine learning and signal processing algorithms for brain-computer interfaces. So again, thank you for going through what you did last night and being able to still come here. Appreciate that very much, and look forward to hearing your presentation.
Yeah, of course. So I currently have new twins at home. Bit of emergency last night, so thank you. If I kind of doze off or forget where I am, just throw a sugar packet at me or something.
Next week.
Yeah. So just to give a quick overview of the company, since you likely haven't heard of it, we're still a very small, about 15-person company. Spun out originally as a quantum computing software company, which I'll touch on slightly. We've now grown to about 15 people, split between Washington, D.C. and Adelaide, Australia, which was a result, again, of our relationship with the quantum computer access. So primarily what we do is these three business areas, and this will touch a bit on the data analytics and the quantum analytics, and not so much the quantum computing software. These are the areas of data analytics I'll cover. Fortunately, I will get to blow through a few of these slides and focus on some of the more interesting areas, as some of this has already been covered. So just start off with the fundamentals. I'm generally not a big fan of the word clouds, but I feel this is an appropriate representation of analytics because you have so many people using it for so many different meanings. When I was at Lockheed Martin, I would go across the company and people would say, yeah, we're doing analytics. Let me show you my spreadsheet, or let me show you my machine learning algorithm, a whole spectrum of how people were using it, what tools they were using, what they were using it for, which Dimitri touched on a bit. The main goal, though, in any case, is to use this vast amount of data we have to more effectively drive decisions. So we've seen a lot of news in recent years about the value that can get returned from data. There are a number of obstacles in actually capturing that data, namely being able to integrate domain knowledge with the analytics and being able to properly frame it for the context of your problem. Just simply predicting an outcome isn't enough to drive value. You have to say, how can you use that outcome? What actions can you prescribe? Dimitri touched on this, so I'll kind of blow through this. This is the same basic concept of having your data acquisition, your storage, your analytics, and then your visualization on top of that. I can't get through this without at least mentioning big data. Not a big fan of the buzzword, but it's used ubiquitously. And it is important to note that there is an explosion in the amount of data that's out there. That's undeniable, and what that allows us to do is have a larger lake to search from, essentially. If you're a fisherman, the bigger the lake, the bigger the possible fish that are in there, but it also makes them harder to find. So big data kind of adds this problem of you're adding a bunch, but is it noise or is it actually a signal of interest? So big data is typically defined by volume, velocity, variety. I made up 3 different V's that I actually care more about: visibility, veracity, and value. That is, do I actually have access to the data? At Lockheed Martin, I didn't oftentimes, even though I worked for the company. Veracity, is it reliable? Do you have missing and invalid entries? And then again, value, is it actually relevant to the problem you're trying to solve? So this has been touched on a bit as well, but this is a common breakdown of data science and what goes into it. And I've kind of separated it into a car analogy. So essentially, you have computer science that gives you the necessary infrastructure and software tools to build upon. This is somewhat similar to the frame of the car. Machine learning really provides the powerful engine to be able to pour through this massive amounts of data in a way that a human wouldn't possibly be able to do. Statistics, often overlooked, extremely necessary to actually validate the results that you're seeing. You'll see a lot of predictions out there from machine learning that are not validated, spurious correlations, overfitting that we'll touch on for a bit. And a lot of that can also be avoided by domain expertise, which again provides the sort of map of where you're going. These are the areas that we focus on for analytics. Starting, you have the descriptive analytics, which is often what you'll see with spreadsheets, looking back at sales from last quarter or whatnot, seeing how did we do. Prescriptive or predictive is where you take that and you want to say, how do you do next quarter? What are our sales likely to look like based on the historical data and the variables that we're currently seeing? Prescriptive to me is where you really start to generate value. That's taking the prediction and saying, okay, this is what I'm likely to see, but how can I manipulate some of these variables to see a more optimal solution? But then once you do that, you run into the problem of adaptive analytics, where once you take those actions to optimize the predicted output, you've then created an additional input into the system. It's no longer a closed system, so you have to take that action that you took and use it as a variable to feed back into future models that you generate. And you have to collect enough data to be able to determine how that action is truly affecting your outcome. So Dimitri touched a bit on this this pipeline as well. The problem assessment typically starts in one of two ways for us. It's either we have a bunch of data, what can we do with it? Or it's we want to achieve this outcome, what data do we need to do so? Data wrangling is essentially the same thing as data cleaning that Dimitri mentioned. Feature engineering, feature extraction, this is actually highly important in being able to create an efficient process where your variables most closely map to your problem of interest rather than just giving the raw data. Deep learning somewhat bypasses the need for this, which we can discuss more in Q&A. Model generation, the machine learning algorithms, model evaluation, the statistical evaluation, and then deployment finally, which often surprises a lot of data scientists when they have to do the actual software engineering to integrate the solution into an existing system. Machine learning, Dimitri touched on this a bit as well. So he described clustering and classification very well. Regression is basically just a continuous version of classification. So rather than predicting discrete outputs, is this a bird or is it a cat or is it a dog? You have a continuous output that you're predicting, such as a stock price. Dimensionality reduction, this is typically used as either a pre-processing or a post-processing step to reduce the dimensionality of your data to make it more manageable for your machine learning algorithms, or to put it in a form where it's easier for a human to visualize the output. So you probably can't see this at this size, but this top graph here is essentially a Swiss roll of data where it spirals around itself like that. And so with it in that form, it's extremely hard to visualize, it's extremely hard to do any analysis on, but dimensionality reduction techniques can take that Swiss roll and actually unwrap it and lay it flat. And at that point, obviously, you're able to visualize the separation in the data much better, and algorithms are much more easily able to process that. So the real power of machine learning is it can go far beyond simple statistical correlation and do it in a much higher dimensional space than what a human analyst can do. So if any of you have a computer science background, you might be familiar with the XOR function. Essentially, all it is you have two inputs, and if they're different, then the output is true, and if they're the same, then the output is false. So if you look at either of these variables by themselves, they're both completely uncorrelated with the output. So if you're doing single variable correlations that you're looking for in your data, you're not going to find anything here. However, if you take the two variables together, 100% can predict the output every single time. So not even all machine learning algorithms are capable of picking up on this, but this is the kind of thing that we're interested in being able to discover. And this is where the true power of machine learning comes in, and being able to do this not for two variables, but possibly over hundreds or thousands, or in some cases, like genomic data, millions of possible variables. The other interesting type of relationship that will often get overlooked with traditional methods is something called explaining away. So this is where you have two variables that are not correlated with each other. They're independent. As an example, say you have an alarm at your home that gets set off by mild earthquakes. And so mild earthquake and your home getting robbed should not impact each other. They're uncorrelated. However, say you're away on vacation and your alarm goes off, you get a call about your alarm going off, you don't know what happened. Was there an earthquake or did my home just get robbed? You're able to go on the internet and look it up and see, oh yeah, there was a mild earthquake in my area. So your knowledge of the earthquake then, through the knowledge of the alarm, just had an impact on your probability that your home was robbed. So these two variables that were previously unconnected now have an effect on the probability that you view of either happening. So I'm going to cover a few of the applications here that from various things that I've worked on that I think might be most interesting. And rather than completely separating the pitfalls into another section, I'm going to mention a few of them with each application. So the first of these, Bill mentioned my doctoral research was in brain-computer interfaces. And so the key objective here was to take neural signals from someone's brain and translate that into a control signal for a prosthetic arm or a computer cursor, a wheelchair, or some other assistive device. So this guy here, this is Tim Hemmes, Hemmes. You can Google him and find some cool videos. Still the most rewarding work I've ever done. This right here, he said, was the first time that he had been able to touch his girlfriend in 7 years, or touch anyone for that matter. He's actually moving the robotic arm there. So there are obviously a lot of complications with this, though. The primary one is, in this case, you have two systems that are adapting to each other. So essentially, you have the machine learning model that is trying to learn what his brain is doing, and at the same time, you have his brain trying to learn what the machine learning model is doing. So if you allow either of those two systems to adapt too quickly, then you end up chasing your own tail, and you never actually converge at a workable solution. The other is imposter signals. There is a lot of noise that gets picked up by these sensors, even the ones that are subcranial. And so one of my favorite examples of this is there was a startup that came out while I was in grad school that gave you a headband. It had two sensors right here on your forehead, and you could concentrate and move things. And it works to an extent. It can definitely pick up neural signals, but for the most part, it's picking up how much you go like that. When you squint your eyes and furrow your brow, the muscular signals in your forehead completely overwhelm any neural signals that it's picking up. So if you're just looking at the data, you see that and you say, oh, that's perfect. That's exactly what I'm looking for. And it requires some domain expertise to know, no, that's not actually what I'm looking for. This wouldn't work in a real environment where maybe the person couldn't move their forehead muscles. And then also contextual awareness. So being able to know where the person is, what they might be thinking about. Doing this in a laboratory is very different than doing it from outside. And you have a lot of other things going on in the brain, obviously. They might be concentrating on moving the arm and then think about what they're going to have for lunch that day.
Can I ask a question?
Sure.
So does the interface, so the brain, you built the interface with the brain, and there's a translation layer to the prosthetic device. Is the machine learning in that translation layer?
Yeah, so the main steps are the signal acquisition, which there are a ton of different recording methodologies right now. I won't go into those. But then cleaning the data, a lot of signal processing DSP that goes into that to remove noise and artifacts and translate it to actual features. So this goes to that feature engineering step, where in this case we're looking at doing a spectral analysis of the signals and seeing how much activity is in each frequency band of the neural signals over time. So you have the frequency band and then the different electrodes. And then those become the features to input into a machine learning algorithm, which then outputs the control signal for whatever you're trying to control.
How much of, I guess roadblock is the wrong word, but effort would be solved by just more accurate sensors?
Quite a bit. So that's definitely one of the big issues, is having enough temporal and spatial resolution in the data. There are some recording modalities that can pick up to the millisecond what's going on. That's what we were using, but the spatial resolution isn't very good. You get a lot of crossover between sensors. Then there are some like magnetoencephalography that can do very good spatial resolution, but the time window is way too long to do any type of real-time control. So that would be a huge advantage in having sensors that could have both high temporal and spatial resolution and be robust to noise.
For macro, it sounds like the greater challenge is in the hardware rather than the math not having enough weapons.
Both, but yes, if I could snap my fingers and have one of the two be perfect, I would say the hardware right now.
So a question on the hardware side, how do you see intracranial implants playing a role in that?
So that's actually what he had. So most of our human subjects were people with intractable epilepsy who were already having subcranial implants to monitor their epilepsy. He was our first subject who he actually had a spinal cord injury and was implanted specifically for this study. But it's definitely a huge advantage versus doing the EEGs that sit on top of the skull, as the skull is essentially a low-pass filter. So you lose those higher frequency bands in the signals that you might be looking for.
And how far are we in terms of getting to implants that are stable over time? Yeah.
Yeah, so the ones that you implant and just record a single neuron, those are kind of the state of the art for a month or so, and then the brain doesn't like having things implanted into it. Essentially, those are a bed of nails that go in the brain, and fatty tissue starts to build up around the sensors, and you lose fidelity. So the ECOG that we used, which is essentially an EEG but sitting beneath the skull, does not have that type of problem, but it's not as good as the single neuron recording. Program management, this is one that I did at Lockheed. What time should I be wrapping up by?
We've got like 7 minutes. And then we'll
Okay, then I'm going to fly through these. This is where we wanted to predict whether a program is going to overrun on cost, fall behind on schedule. Got some great results. One of the biggest issues in something like this, though, is simply cultural acceptance. You might have the best model, the best value of anything that has ever been created for this purpose, and if you can't convince the stakeholders why, if you can't put it in their language, it flat doesn't matter. And this was a huge one because we had program managers who had been doing it this way for 30 years. And it was low risk the way that they were doing it. Their customer accepted the way that they were doing it. So why should they change to this black box machine learning system that they had no idea what was going on inside? So that's a big issue. And then also being able to take the output and input it into a higher level systems optimization. So if I take action to increasing staffing here, how does that affect my staffing and budget over here, and so on. So again, it's not a single output that's able to inform your actions. Market analysis for portfolio optimization. This is a fairly well studied one. Primary problems are being able, again, to incorporate existing domain models. So you may not have enough data to do a purely data-driven system. So how can you integrate it with existing rules-based models that people have developed over 30 years? So rather than flat replacing them, you have them work together. Primary problem here, non-stationary data. What the stock market has done for the past 10 years is not necessarily what it's going to do for the next 10. Every mutual fund you ever buy is going to have a disclaimer that says that. It's the same problem. Huge issue at Lockheed Martin, predictive maintenance. So how can we better predict when parts are going to fail so that we can optimize our supply chain, optimize storage of spare parts, and optimize maintenance to minimize downtime and minimize costs. So this is similar to what your car has now. Instead of, hey, change the oil every 3,000 miles, takes into account driving conditions, mileage, temperature, all these variables that then give you a warning light and beep at you and say, hey, change your oil. I'm going to kind of skip over this one because it might take a bit longer to explain, but basically this is for looking for data discovery. So using a model to tell you what data you still need to collect in a case where data collection is difficult. So this is for clinical trials mostly, where rather than blindly enrolling 100 people, studying them for 6 months and so on, you can look at the data you already have and determine which 100 people will give you the most information, so that you can more quickly get through that. Sports analytics, predicting outcomes of games. You can see this on ESPN and fantasy apps and whatnot all the time. Market segmentation. This is quite similar to what Dimitri mentioned with Obama's campaign, and actually Trump's campaign did a very large amount of this as well. Last night was both an enormous failure and an enormous success of data analytics, and that obviously all of the polls were wrong, save Nate Silver's was the closest. He had a 30% chance of him winning, and he was probably the most data science-like poll, and he got very criticized for giving as high as 30% chance. But on the other side, Donald Trump had a very, very well-organized and sophisticated campaign to identify how to communicate with various voters. Anomaly detection for mobile device integrity. So this is looking at data on your phone to do transparent authentication, how you're holding it, where you are, what Bluetooth it's connected to, and so forth. And we have high interest now in using machine learning to do quantification of cyber risk. So very interested in discussing that later with anyone, or we're actually hiring in that if you know anyone with a cybersecurity background who wants to get into data analytics. Very interesting presentation, by the way, Ed. And then identification of leading indicators in open data. This was also touched on a bit, looking at social media, news articles and such, to be able to pick up on events and really unstructured data, text, voice, video, the amount of it is enormous compared to the structured data that's out there. And we haven't even seen the tip of the iceberg as far as being able to effectively analyze this unstructured data. Deep learning also very good at that, again, as it's able to do its own features. So these are the other pitfalls that I will quickly mention. As Dimitri already mentioned a lot of these, overfitting is the biggest problem, where you have a set of data and you train a model to it and the model learns exactly what those data points look like. But it then doesn't have any generalizability to actually be applied to future data that is similar but not exactly the same. And so in this example down here, you can see you have these blue data points. The green line is the function that actually generated the data points. The blue line is what the model is determining. So here you're underfit, here you're overfit, where your model goes through every single possible data point. But you can see right here there's a huge problem, because now if you get a new data point that is right here, your model is going to predict the y value to be this, when really it should be, this. So you want your model to fit to the data, but not so perfectly that it can't fit to new unseen data. Cursive dimensionality, huge issue again with big data. The more data you get, the number of samples you need explodes exponentially. You can kind of think of this as if you have two data points, you can perfectly define a line that goes through them. If you go to 3 dimensions and you still only have 2 data points, there are a lot of planes that can go through those data points. If you go to 4 dimensions, even more possibilities. And you can see it becomes much harder to determine what the actual function that generated those 2 data points is as you increase the dimensionality. Sampling bias, extremely common, where you have 99% of your data points are from one class for something like anomaly detection, which is often what machine learning is trying to do. The algorithms are very smart and can say, oh, I noticed that 99% of your data points come from class A. So I'm just going to predict class A every single time, and I'm going to be 99% right. That's pretty good. So that's something that you've really got to look out for. Corrupt, missing, and invalid data, huge problem with real data. We like to think that all of our data is clean and perfect, but it often has fat-fingered entries or missing values or faulty sensors or the like. Again, leaving out domain expertise, huge issue. Dimitri touched a bit on confounding variables. And I don't know if you can read this comic from here, but again, data analytics is such a hot buzz topic area that people want to just throw it at any data set or at any problem they have. And if you haven't actually formulated what the problem is and what the value is that you want to get out of it, then you just have a cool experiment that you're doing. And that's probably not going to keep getting funded in the long term. You end up with things like the AI winter, where people say, okay, what can I do with this? And you say nothing, and then they get disappointed and cut all your funding. Algorithm selection, there are a ton of algorithms out there. This is from a Python scikit-learn package, just to kind of show you what can often go into selecting the best algorithm. My favorite is right here. You can end up at a spot that says tough luck. But a lot of this also ends up being trial and error. I was going to touch a bit on quantum computing's impact of machine learning. I think I'm probably out of time and we can move to Q&A.
So I don't mind. It's really, I wanted to end it at 2, not for my purposes, but to respect everybody's time. But I would like to learn about quantum computing. Is everybody okay with that? And then if we have some Q&A, if you want to stay after and query speakers, feel free to do that. So yeah, let's learn about quantum computing.
So some of these were already touched on, but areas where data analytics will continue to improve, we'll continue to see more data, increased accessibility, and again, looking at new types of data, text and sound and video and whatnot, better algorithms. We've touched on deep learning, being able to tune the hyperparameters, obviously, or automatically. Deep learning has a lot of knobs to turn to get the best result for each problem, and being able to more intelligently do that is a huge issue, especially since deep learning, as mentioned, takes forever and a day to train. But what I'm really going to touch on here is the better hardware piece. GPUs were discussed, which are a huge boon for deep learning. Custom FPGAs are getting made now as well. But then quantum computing I'll discuss, and really in the end we're going to have hybrid systems that leverage the best of each of these pieces of hardware for specific parts of the problem. As a good preface to quantum computing is that you will never have a quantum computing laptop sitting on your desk that you're going to run Firefox and Microsoft Word in. They're very specialized machines that do very specialized types of problems and require their chip to be at currently 15 millikelvin is where the D-Wave processor sits, which is colder than deep space. So quantum computers exploit a few key quantum mechanical effects. The one that you've probably heard the most of is superposition. Thought I had another slide on that. Apparently I don't. Superposition is essentially where instead of having each bit be a 0 or a 1, it can be a 0 and a 1 at the same time, is how it's explained. What's actually true is that it has some probability of being a 0 or a 1. So you can manipulate what that probability is through your problem formulation, and then you run the problem a whole bunch of times and you can see the distribution of your output. So that is superposition. Schrodinger's cat is the common example of explaining that. I'll let you Wikipedia that if you want to. Entanglement is also extremely important, as it's what allows multiple quantum bits or qubits to interact with each other. So once one qubit becomes either a 0 or a 1, then the entire system collapses into a deterministic state. So entanglement allows how one bit collapses to impact how other bits collapse. Einstein called this spooky action at a distance, and he didn't really understand what was going on there, and I'm not going to pretend I do either. The example that I commonly give is, say you have a red ball and a blue ball, and you hide them both, close your eyes, put one of them in a box, and the box gets shipped off to California. Someone opens it and says, "Oh, hey, I've got a red ball." You then know that your ball was blue, even though before you knew that, you just had a 50% odds that your ball was blue. Quantum tunneling is what the D-Wave quantum computing device uses. This is very similar. It uses quantum annealing, which is very similar to simulated annealing, except rather than having to go up and over energy barriers, you can actually tunnel through them. And so this is how Google was able to release something last December where they claimed 10 to the 8th speed up on a problem. There are a lot of caveats with that. It was a very, very specifically defined problem that had a lot of high, narrow energy barriers that were able to specifically make use of this quantum tunneling effect. And it was a constant factor speed up. It wasn't a scaling speed up. So, if you have an algorithm that is scaling at 2 to the n, 10 to the n, 10 to the 50th is intractable, 10 to the 42nd is also very intractable. So for this really to be powerful, you need that scalability in the speed up. So machine learning has been proposed as one of the killer apps for quantum computing, the same way that like the spreadsheet was kind of the killer app for the original classical computer that started to get them on everyone's desk. There is a book by Peter Wittick called Quantum Machine Learning, appropriately enough, that is actually quite short and quite accessible. It gives an explanation of quantum computing and machine learning. Don't require, you know, a Ph.D. in either area. I'm not going to say it's easy reading, but if you want more background on the topic, that would be a good thing to check out. This table here is from that book of known speedups that have been exhibited for quantum computers, and this is sort of where we are in quantum computing. We are developing algorithms that have proven theoretical speedup so that once the hardware is fully mature, those algorithms can be dropped on it and go. The most famous of those is Shor's algorithm, which is going to crush RSA encryption, but the hardware isn't ready for that yet. And quantum also provides unbreakable encryption through another method, but that's a whole other topic. So a lot of these are very interesting. They're theoretically valuable, but some of them also, you know, I don't know what I'm going to do with a speed up of k-means. That's kind of the algorithm I use when I want a quick and dirty answer, and more effective algorithms are too computationally costly to do anything. So a few of them that will be useful. So next to Shor's algorithm, Grover's algorithm is the, I would say, second most famous quantum computing algorithm. What this does is it allows you to search an unsorted database in big O of square root of n time, versus the best known classical solution is big O of n. So you're getting this quadratic speed up on this, and searching for something in an unsorted database is a foundational part of a lot of machine learning algorithms. So a lot of machine learning algorithms can take this and build on top of it. And I won't try to explain Grover's here. This is some work that we did at Lockheed that actually shows promising speed up on deep learning using the D-Wave chip. So on the left here is convergence using a classical method, contrastive divergence, and on the right here is using the D-Wave chip. So you can see we get much, it converges much more quickly and with much lower variance based on the number of iterations. If you stretch this out farther, it will eventually converge as well. But that's not shown here for, you know, visibility. These are some other things that we have done. So L0 penalized regression. This is something L0 penalty does automatic feature selection by being able to penalize the weight of a variable directly. So it forces a sparse solution. However, the L0 penalty is non-differentiable and highly difficult to solve for classically. So we have a quantum solution that has done this. Graph analysis is, there's a paper by Lucas 2014 that essentially takes all of CARP's 21 NP complete problems, mainly graph analysis, and has quantum solutions for them. So this is another area that is of huge interest for social network analysis, cybersecurity. Really, a lot of things can be viewed as a graph, but it's very computationally difficult to do things like finding matching areas within a large graph. Yeah, I think that was, we'll stop there. So summary on quantum computing, it's has high potential for machine learning. Hardware, the universal type that's going to do Shor's algorithm is still at least 5 to 10 years away, but we're developing algorithms to show what it can do so that the software and the hardware are ready at the same time rather than hardware's ready and then let's take another 10 years to do the software.
Thank you, John.
Yep.
Grab this one.
Sure.
And I want to thank everybody for coming today. John, Dimitri, Edward, thank you so much for educating us and spending some time with us. And feel free to ask any questions. I'll be hanging out here, but we're at the 2 o'clock time frame right now. But if there's any questions, feel free. The guys can come up and answer anyone you might have.